Bismillah, welcome to Think Math. Today we start a brand new topic, differentiation. We have already seen how to measure the average rate of change of a function over an interval. Now we ask what happens at a single point. In this lesson, we will understand the geometric meaning of the rate of change, define the first derivative of a function, and explore the relation between differentiation and continuity. Let's look at the graph of a function and the point on that curve at x1. If we draw the tangent line at that point, the slope of that tangent line, that's tan alpha, is given by this limit. The limit as h approaches 0 of f of x1 plus h minus f of x1 all over h. This is exactly the rate of change of the function at that single point x1. Let's make this a formal definition. For a function f defined on an open interval from a to b and x inside that interval, we define f prime of x as the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that the limit actually exists. This is called the first derivative of f of x. We write it in several ways, and the most common ones are dy of dx, f prime of x, or d by dx of f of x. They all mean the same thing. We can also write the derivative as the limit of the difference quotient f prime of a equals limit as x approaches a, f of x minus f of a all over x minus a. This is the same idea, the slope of the second lines approaching the tangent slope, and it's the form we'll use for one-sided derivatives in piecewise functions. Now, when do we say a function is differentiable at a specific point x equals a? We say f is differentiable at a, where a is in the domain of f, if and only if f prime of a exists. Using this same limit definition, here is the key definition. We need the derivative from the right f prime of a plus to equal the derivative from the left f prime of a minus. If they are equal, f is differentiable at a. But if they are not equal, then f is not differentiable at that point, even if the function looks fine otherwise. Here's an important relationship. If a function y equals f of x is differentiable at x equals a, then f must be continuous at x equals a. But, and this is crucial, the converse is not always true. A function can be perfectly continuous at a point and still fail to be differentiable there. We'll see a clear example of that later in the lesson. Let's put this into practice. Take f of x equals x squared plus 2x minus 5. We want to find f prime of x and then the equation of the tangent line at the point 3 and 10. Start from the definition, f prime of x equals the limit as h approaches 0 of f of x plus h minus f of x all over h. First expand f of x plus h, that's x plus h all squared, plus 2 times x plus h minus 5. Expanding the square, x plus h squared equals x squared plus 2xh plus h squared. So f of x plus h becomes x squared plus 2xh plus h squared plus 2x plus 2h minus 5. Now subtract f of x. The x squared and the minus 5 cancel with the original function, leaving us with 2xh plus h squared plus 2h. Divide everything by h, we get 2x plus h plus 2. Now take the limit as h goes to 0. The h term vanishes and we are left with f prime of x equals 2x plus 2. To find the slope of the tangent at x equals 3, substitute f prime of 3 equals 2 times 3 plus 2, which is 8. Finally, using the point slope form with the point 3 and 10 and the slope equal to 8, y minus 10 equals 8 times x minus 3, which simplifies to y equals 8x minus 14. That's our tangent line. Now let's discuss differentiability at x equals 1 for two different functions. Part A, f of x equals x minus 2 over x plus 3. First, f of 1 equals 1 minus 2 over 1 plus 3, which is negative 1 quarter. Now set up the derivative definition. F prime of 1 equals the limit as h approaches 0 of f of 1 plus h minus f of 1 over h. Substituting f of 1 plus h equals h minus 1 over h plus 4. Now we combine this with negative 1 quarter over a common denominator, multiplying out the numerator 4 times h minus 1 plus h plus 4 all over 4 times h plus 4. This simplifies in the numerator to 5h, giving us 5h over 4h times h plus 4. The h cancels, leaving 5 over 4 times h plus 4. Taking the limit as h approaches 0, f prime of 1 equals 5 over 16. Since this limit exists, f is differentiable at x equals 1. Now part B. R of x equals the square root of x plus 3. R of 1 equals the square root of 4, which is 2. Set up the definition. R prime of 1 equals the limit as h goes to 0 of the square root of 4 plus h minus 2 over h. This has a classic 0 over 0 form, so we multiply by the conjugate. Square root of 4 plus h plus 2 over itself. In the numerator, this becomes 4 plus h minus 4, which is just 4. So we are left with h over h times square root of 4 plus h plus 2. The h cancels, giving us 1 over square root of 4 plus h plus 2. Taking the limit as h goes to 0, r prime of 1 equals 1 over 4. Since this exists, r is also differentiable at x equals 1. Let's try another one. F of x equals the square root of x plus 5. We want f prime of x, then evaluate it at x equals 1 and x equals 9. From the definition, f prime of x equals the limit as h approaches 0 of square root of x plus h plus 5 minus square root of x plus 5 all over h. The plus 5's cancel immediately, leaving square root of x plus h minus square root of x over h. Again, we multiply by the conjugate, square root of x plus h plus square root of x over itself. The numerator becomes x plus h minus x, which is just h, so we get h over h times square root of x plus h plus square root of x. Cancel the h's, we are left with 1 over square root of x plus h plus square root of x. Taking the limit as h goes to 0, f prime of x equals 1 over 2 root x. Now evaluate f prime of 1 equals 1 over 2 times root 1, which is 1 half. And f prime of 9 equals 1 over 2 times root 9, which is 1/6. Our final example has 3 parts, and each one teaches something different about continuity and differentiability. Part A, f of x equals 2x minus 5 when x is at least 2, and 2x plus 5 when x is less than 2. We check x equals 2. The limit from the left, as x approaches 2 from below, f of x approaches 2 times 2 plus 5, which is 9. The limit from the right, as x approaches 2 from above, f of x approaches 2 times 2 minus 5, which is negative 1. Since 9 does not equal negative 1, the limit does not exist at x equals 2. This means f is not even continuous at x equals 2, and if it's not continuous, it cannot be differentiable there either. F of x equals x squared plus 2x when x is at most 1, and 4x minus 1 when x is greater than 1. Check x equals 1. First, f of 1 equals 1 squared plus 2 times 1, which is 3. The limit from the right, 4 times 1 minus 1 equals 3, which matches f of 1, so it is continuous at x equals 1. Now for differentiability, we'll compute the left and right derivatives separately. From the left, f prime of 1 minus equals the limit as x approaches 1 from below, x squared plus 2x minus 3 over x minus 1. Factor of the numerator, x squared plus 2x minus 3 equals x minus 1 times x plus 3. The x minus 1 cancels, and taking the limit gives us x plus 3, which is 4. F prime of 1 plus gives the limit as x approaches 1 from above. 4x minus 1 minus 3 over x minus 1, which simplifies to 4 times x minus 1 over x minus 1, giving exactly 4. Since both one-sided derivatives equal 4, it is differentiable at x equals 1. Part C, f of x equals the absolute value of x minus 3. Check x equals 3. We can rewrite this piecewise. X minus 3 when x is at least 3, and 3 minus x when x is less than 3. The right derivative, f prime of 3 plus, equals the limit of x minus 3 over x minus 3, which is simply 1. The left derivative, f prime of 3 minus, equals the limit of 3 minus x over x minus 3, which simplifies to negative 1. Since 1 does not equal negative 1, f is not differentiable at x equals 3, even though the absolute value function is perfectly continuous there. This is our clearest example of a function that's continuous but not differentiable at a point. Now it's your turn. Here are three problems to work through. 1. A piecewise function that's continuous at x equals 2. Find the missing constant a. Then check whether it is also differentiable there. 2. A piecewise function involving cosine. Discuss its differentiability at x equals pi over 2. 3. Given f of x equals ax squared plus b, and the tangent to the curve at the point 1 and negative 1 has a slope of 8. Find the values of a and b. Pause the video and give them a try before moving on. Now let's quickly review the answers to the exercises from the last lesson. And that ends our introduction to differentiation. We have defined the derivative from first principles, connected it to the geometric idea of a tangent slope, and we have seen how differentiability relates to, but stronger than, continuity. In the next lesson, we'll learn the rules of differentiation, so we don't have to go back to the limit definition every single time. Thanks for watching, and see you in the next lesson.